So we need to talk a little bit here in nuclear chemistry about two concepts that I know that you've already discovered or discussed before, which are fission and fusion. And these are special types of nuclear reactions that we actually can use mostly for energy. So the first one we want to look at is fission. And fission is defined as the splitting of heavy or large nuclei into lighter or smaller nuclei. Now, this is the type of reaction that is done in nuclear power plants, like the one down at 3 Mile Island, the one over in Chernobyl that we had a problem with. So these are the ones that we actually use to generate electricity here on Earth. So fission reactions, you start with a large element, like uranium-235 or plutonium-239. So not all elements are capable of undergoing fission, so you have to be very careful. For instance, not all atoms of uranium can undergo fission, and not all atoms of the element plutonium can undergo fission either. What happens is we start off hitting the nucleus with a neutron, and the neutron gets absorbed into the nucleus, causes it to become unstable, and the nucleus splits. So we get two smaller medium-weight nuclei, some extra neutrons, and lots of energy. So here is an example of a fission reaction. So you can see I'm starting here with uranium-235, and I hit it with a neutron, and I get krypton-91, barium-136, and then I get these extra neutrons. What's not on here is the energy that is released, and that's actually what we end up harvesting or using here for our needs to generate electricity. Now, those extra neutrons create something called a chain reaction. And so what does that mean? Well, basically the chain reaction means that that with those neutrons, we can actually take them and use them to start the next reaction. So for instance, if I start with a single neutron here, let me see if I can get it to go. All right, not that, there we go. If I start with a single neutron, okay, that goes and it hits a nucleus, it becomes unstable, and then the nucleus splits. But what I get coming off of that is 3 more neutrons. Each of those neutrons can then go and hit its own nucleus, and each of them give off 3. So as you can see, this continues to grow and grow and grow. So once I start this reaction, it just continues all by itself. Now, this quickly grows very, very large, and when it grows very large like that, it can actually get out of control. And so if it becomes an uncontrolled reaction, that's something actually that we don't want happening, for instance, in our nuclear power plants. So what we do is, within the nuclear power plants, is we actually have these things called control rods that absorb some of these extra neutrons. So if I absorb that neutron, then all of this doesn't happen. Okay, and then I could absorb this one, and then it will only split off 2, and maybe I absorb this one, these 2 here, and that will only split off 1, which is much more controllable. So we keep the reaction going, but it doesn't get crazy. However, there is a use for this uncontrolled chain reaction, and that is what we use for fission bombs. So that's the only time we really would want that to get out of control, but unfortunately sometimes that actually happens, and we don't intend it to. That's what actually happened at Chernobyl back in the 90s. The big problem with fission that we have is not that we can't produce it, it's not that it can get out of control, it's the disposal of the waste. The waste that is generated actually has a very long half-life, and so it stays radioactive, and it stays radioactive for a very, very long time. So one of the challenges that we have moving forward is, what do we do with this? And there's several schools of thought. The first one is the current one that we have, which is all right, so like I was saying, the waste has a very long half-life and is very radioactive. So the two schools of thought, one would be to actually have the nuclear power plants actually keep all of their spent radioactive fuel and the waste on site, which is what they currently do. There's another school of thought that we need to actually collect all of this and keep it in a single place so we can watch over it, because this stuff could be used by people who maybe have some harmful intentions towards us to spread radiation and cause people to get sick from the radiation over a very large period or very large area, like with a dirty bomb or something like that. So unfortunately, the plans that they've put forth for the central place to keep it, there's a lot of questions. How do we get it there? Is this a really good place to do it? There's been some questions about it. So right now we're sticking with the current plan of each location holding on to its own radioactive material and waste. In addition, fission produces a lot of thermal pollution, and what that means is heat. If you look at any of the nuclear power plants that are around, all of them are on water sources. If you think of 3 Mile Island, it's on the Susquehanna River. And basically there are two water connections between the plant and the Susquehanna. One is a water intake, so it actually brings water into the facility. And just so you guys are aware, the water that we bring in from the Susquehanna never actually comes in contact with any radioactive material. All of the water that actually comes in contact with radioactive material stays within a very sealed, closed system and is not released into the environment. But what they do is they use that water to heat it up, generate steam to turn the turbines to generate electricity. Then they set that water in those big cooling towers, and you'll see the steam coming off of those cooling towers as the water sits in there to cool. And when it has cooled down enough, they will then release it out through the other connection back into the environment. Well, while they let it cool down very close to the temperature, it's never quite exactly the temperature. So when you release that warmer water back into the Susquehanna, it actually disrupts some of the ecosystems in that area. And you'll find that everywhere with all the nuclear power plants. So that is a concern. So the other type of reaction is fusion, and you can think of this basically as the opposite of fission. If fission is splitting of the nucleus, then fusion is literally fusing together of the nucleus. But these are different nuclei. We actually find this happening on the sun and other stars. So if you think about the sun, it's very high temperature, it's very hot, and this is actually a problem because generating the same environment to allow fusion to happen is not that easy to do here on Earth. And until we can conquer this problem, using and creating fusion here on Earth is not something that is easy to do. Fusion involves small nuclei, so we're talking about tiny atoms rather than large atoms, hydrogen and helium. So why would we want to use it? Well, it gives us more energy, first of all. So fission gives us a lot of energy, but fusion gives us even more. And then the products that we make are not highly radioactive, so we don't have that waste issue that we were talking about before. Here's an example of fusion. So I've got two different forms of hydrogen, two different isotopes, fusing to form helium, which is, very safe, and then a neutron. All right, so that concludes our discussion about fission and fusion, and the last little bit that we will talk about has to do with the uses of radioisotopes and how it benefits us as humans.